Hello everyone. I am Hanjae Kim from Samsung Research. I'll be talking to you about Document AI Universal Document. In this presentation, I'll introduce what Document AI is and the detailed components, technologies that make up Document AI, and also show the document analysis result of the model we have developed. First, let me begin with the introduction to Document AI. Document AI can be defined in various ways. As we see it, Document AI refers to a technology that acquires diverse information within documents through document processing and then delivers this information to an LLM to generate answers. The goal of Document AI is to contribute to improving internal productivity by reducing the amount of the time users spend searching for information. When we defined problem and began developing Document AI, one of the major challenges we encountered was diversity of internal documents. Internal documents are not limited to text-only reports. They also include invoices in table format, Excel sheets, PowerPoint slides that contains graphic information such as image and chart. Understanding unstructured documents can be viewed as understanding three aspects. First, identifying what the components of the documents are. Second, determining where those components are located. Third, and lastly, understanding the relationship among those components. In particular, since documents often contains both text and image information, it is essential to also consider the relationship across different modalities. From these motivations, we have summarized what we believe constitute a successful document AI, and there was a question previously delivered to us, so let me tell you about the answer first of all. I have shared with you the result, and also I told you that we'd like to enhance the productivity. So forcefully, instead of standardizing all the documents, it is important to develop the algorithm that can be applied to different methods, and that should be the document AI direction. So that's what we are currently trying to develop. So here, what are the successful document AI? Let me summarize what are the successful document AI. First, as mentioned earlier, optimized analysis models are needed for various types of data that documents can contain. Second, in order to improve productivity, lightweight network models are required that can process large volumes of document quickly. Finally, an information processing procedure, specifically a chunking strategy, is necessary for effective multimodal data retrieval and interleaved generation. To achieve these three objectives, we have designed the following end-to-end flow. When document is input, it is parsed in short time through three lightweight models. The data is then chunked. Relationships are inferred, and finally, a retrieval generation process is performed to enable question and answering. From next slide, I will explain our parser framework. To achieve these three objectives, we have designed the following end-to-end flow. When document is ingested, it is parsed within short time using three light-weighted models. The data is then chunked, relationship are inferred, and finally retrieve generation is performed. There was a question, and using one VLM, we can do the parsing. Well, we have considered that direction as well. As a result of our analysis, using one integrated VLM, it's far better to use more quantified small sub-model, light-weighted model in terms of the accuracy, in terms of the processing speed. Therefore, OCR, layout detector, and table recognizer, which are the models they use to conduct document parser. Let me take a look at one by one. First, OCR. Since internal documents exist in multiple languages such as Korean, English, and Chinese, we use OCR models specialized for each language type in order to ensure accuracy. At this point, it is necessary to determine which OCR model a given language image should be processed by. To this end, we develop a lightweight language identifier. This language identifier was trained using synthetic data, thereby reducing the burden of data acquisition. Acting as a router, it directs each language image to the appropriate specialized OCR model, thus enabling accurate multilingual OCR. Now, next is layout detector. Layout detector, well, it is important to understand the layout comprehensions. Layout refers to the components that make up documents such as paragraphs, tables, and image. To identify the locations and type of this layout, we employ layout detector. Well, using annotated documents, the layout detector is trained to recognize the bounding boxes that indicate the positions of each layout elements as well as their types. Finally, this table recognizer not only identifies the text inside a table, but also understands the table structure, thereby determining which category each piece of text belongs to. Lastly is a table recognizer. Table recognizer, when a table image is given, table recognizer interprets the table structure in HTML format and by applying OCR to the table image, converts the text into the data that is inserted into these corresponding cells. And that's how we input all the data. So we restructure the table. One of the unique thing is that when the table is integrated or when there's an image inside the table, then when the images are embedded within the table, they are placed into appropriate empty cells to complete the table. The parsing results produced by these models are as follow. This is the paper picture, not only text but also image, and tables are successfully processed with OCR and layout detection. Even when text and image informations are embedded inside a table, we confirm that the table is correctly structured and we can easily understand what are these, and then the relationship between text and image we can comprehend. From next slide, I will explain data chunking. Data chunking refers to the process of gathering and refining large amounts of information extracted from documents in order to make them more suitable for search and question answering. Therefore, when performing chunking, it is important to test retrieval and generation result in parallel and find the appropriate chunking method. Well, the main challenge here is image. When generation is performed to output both image and text together, it is necessary to determine which text chunks each image corresponds to. For example, in this case, the blue image should be connected with the bottom chunk containing vacuum cleaner reset information. The way this relevance is quantified significantly affects the connection result. Typically, the relevance between the image and the text chunk is measured by similarity. There are several ways to make the determination using multimodal embedding, projecting both into joint embedding space, and then measuring the distance between the embedding. That could be one way, or using captioning or OCR extracted information from the image to generate text embedding and then measuring similarity between text embedding. By combining multiple similarity measurement method, the accuracy of similarity estimation can be improved. This allows us to quantify the similarity and determine which text chunks a given image modifies or describes. Next, I'll move on to the information retrieval steps, which find information relevant to the user's questions for questioning answers. Similar to how we measure similarity between image and text, multiple search methods are combined to identify information related to the query. The two most common methods are keyword search, which excel at precisely capturing information containing specific keywords, and dense search, which uses embedding to capture semantically similar information even when expressed differently. So we call this as a dense search. Keyword search is effective for exact matches but weak at finding semantically similar but lexically different expressions, and dense search can complement this limitation. Fusion is performed by weighting and combining the search score from each method. Typically, fixed weights are used, but we found that the performance varies significantly depending on which search method is emphasized, which in turn depends on the characteristic of the document. For example, if a document contains large amount of domain-specific terminology, keyword search may be more effective, whereas in cases with many synonyms, dense search proves more useful. Based on this finding, we are developing a technique to adapt or to adjust the weight depending on the type of information contained in the document. Finally, I'll conclude this presentation by showing you the question answering result generated through the previously described chunking and retrieval process. As shown in the pipeline on the left, we define the data based on the inferred image-text relationship and provide it to the LLM in a way that it can understand. This enables multimodal rec or retrieval augmented generation, which can generate interleaved outputs of image and text. As shown in the result image on this right, users are able to intuitively view not only the text responses but also relate charts and image together. Such generation results are highly dependent on the inference of image-text relationship. By linking examples image to the descriptive text in each step and delivering this to the LLM, the model can generate text along with the corresponding image that is connected to the text. Through this approach, users are expected to search and analyze complex documents more quickly and in greater depth, thereby contributing to improved productivity within the organization. That concludes my presentation. Thank you.